Morning. Last time we talked about power series and how you could write a function of x as a series and then determine for what values of x does it converge. Now we're going to look at a special set of series called the Taylor series expansion. All right, now what the Taylor series expansion allows us to do is take a function that has infinite differentiability. In other words, a function whose derivatives always exist. Certain functions like that are sine x, cosine x, hyperbolic sine, hyperbolic cosine, tangent, hyperbolic tangent, e to the x. All of those you can take derivatives as long as you want. And we're going to use that fact to determine a series expansion for them. You might ask yourself, why are we interested in series expansion of these transcendental functions? And the answer is, how do you think your calculator computes e to the x? Calculators can only do addition, subtraction, multiplication, and division, and yet e to the x is a transcendental function. It cannot be represented as a polynomial of finite degree. But Taylor series expansion allows us to represent it as a polynomial, if you will, of infinite degree. All right, and here's the way we do it. So suppose f, our function, has as many derivatives as we want. Well, the fundamental theorem of calculus says that if I go from a to x of f prime of t dt, f prime now, right? What does that equal to? Well, it's the antiderivative of f prime evaluated at x, subtract the antiderivative of f prime evaluated at a. But the antiderivative of f prime is just the function f. All right, so the fundamental theorem of calculus tells us this, that the integral from a to x of f prime of t dt is f of x minus f of a, no big deal. Now what we're going to do is we're going to solve for f of x. So f of x is, just pull f of a over to the other side, and I get this. It is f of a plus the integral from a to x of f of t dt. Now what I'm going to do is a pretty interesting thing. I'm going to take this integral and I'm going to use integration by parts. Okay, and so integration by parts, I have to let u be something and dv has to be something else. Well, I'm going to let u be, and by the way, maybe we should make this correction now. This is f prime. All right, so I'm going to let u be f prime, and then dv has to be everything else. Well, everything else is just dt. All right, so u is f prime, dv is dt. So what's du? And the answer is du is f double prime t dt. Just take a derivative. Now what's v? Well, v is the integral of dt, which is t, right? Usually when we do integration by parts, that's all we do. We write t. But now you know that antiderivatives, I can add an arbitrary constant. Well, the arbitrary constant I'm going to add in this case is minus x. T is my variable here. X is acting like a constant. Okay, I can add any constant I want, but the constant I'm going to add is minus x, y, because I know where I'm headed. All right, so integration by parts says what? I have f of a And then I write what? U times V. So here's my U times V. Now it's a definite integral, so I have to evaluate it between A and X. Minus the integral of V, what's V? T minus X, du, and what's du? F double prime of T dt. All right, so there's my integration by parts formula. Now, when I plug in X here, the upper bound, I get what? X minus X, that's 0, that goes away. When I plug in A, well, since it's the lower bound, I have a minus here. And I get A minus X. So I get, when I plug in these values, because this is a definite integral, this is what I get. What's left is this thing. Right? Now, I'm going to move the minus sign inside, and it's instead of T minus X, I'm going to write that as X minus T. And this is times F double prime so there's another prime here. All right. F double prime of T dt. All right. Now guess what I'm going to do? The answer is I'm going to do it again. So I'm going to integrate by parts here one more time. Okay, so what's u? U is F double prime of T dt, so what's du? Well, du is one more derivative, which is F triple prime of T. All right, now I'm going to be doing this enough to where I'm going to have too many primes, so my notation is F upper 3, see that right there? Means 3 derivatives, right? F upper 1 would mean 1 derivative, and F upper 0 would mean no derivatives, which means I just have my function. All right, so u is equal to F double prime. What's du? F triple prime. dv is everything that's left, which is X minus T dt. All right, now T, remember, is my variable. So I'm going to have to integrate that to get V. So what is V? V is the integral of that. I do it by u substitution. I'm going to let u be X minus T. du is minus dt, and when you do the work, you're going to figure out that V is minus X minus T squared over 2. All right, now I'm just going to write this integral by my integration by parts formula again. So I have this term comes down, this term comes down, and now writing this integral is going to be what? U, that's this, times V. So it's U, which is F double prime of T, times V, which is minus X minus T squared over 2, evaluated again between A and X, and then minus the integral of V, which is another minus, du, which is F upper 3 T dt. All right, now when I clean this up, these two minuses go away. I get a plus. When I plug in X at the top, I get 0. When I plug in A at the bottom, I'm going to get X minus A, and this minus goes away because it's going to be minus a minus. So now I'm down to here with this thing again. Guess what I'm going to do? I'm going to do parts on this again, where u is this now, F upper 3, so what's du? F upper 4. V has got to be everything else, or rather dv. Well, So dv has got to be everything else, which is this dt. And when I integrate that, I'm going to get x minus t cubed over, it kicks out a 3 downstairs. All right, you get the idea? So I just continue to do that. What I get is, and now I've just rewritten things in a kind of a clever fashion so that you can see the pattern. What's f of a? Well, f of a is f upper 0 of a. Remember, no derivative. I can write that f upper 0 of a over what 0 factorial. Now there's nothing else in this term, but I could write it as x minus a to the 0, because that's 1. And then this is f upper 1 of a, x minus a to the 1 over 1 factorial. The next one is f upper 2 of a, x minus a squared over 2 factorial. Do you see a pattern? The next one, when I clean this up, is going to be f upper 3 of a, x minus a cubed over 3 factorial. That's after I plug all this stuff in. So the bottom line is this, right? If f is infinitely differentiable, then I get the Taylor expansion of f. And what is it? The nth derivative of f evaluated at a over n factorial times x minus a to the n, and n runs from 0 to infinity. Guess what that is? That, my friends, is a power series, just like the kind we talked about last time. All right, so that's the story of Taylor expansions. They're a special case of Taylor expansions is called the Maclaurin series expansion. And the Maclaurin series expansion is the Taylor expansion when a is equal to 0. And we say it's the Taylor expansion about a equals 0. So what does that mean? If it's the Taylor expansion about a equals 0, it means that when I take this formula right here and I plug in a equals 0, that's the Maclaurin expansion. All right, so it's going to be f upper n at 0 times what? X minus 0 to the n, but x minus 0 is just x, all over n factorial. So the Maclaurin expansion is the summation in running from 0 to infinity of f upper n evaluated at 0 divided by n factorial times x to the n. Get it? Where n runs from 0 to infinity.